Okay, in this video we begin to take a look at the force of static friction. Like from earlier, the force of kinetic friction, the force of static friction also obeys some simple empirical properties. Let's list those first. Empirical properties of static friction. Okay, first of all, the force of static friction acting upon an object always opposes the direction that the object would tend to move. Force of static friction acting upon an object always opposes direction that the object would tend to move. Okay, now let me illustrate what I mean by that. This is actually intuitively obvious. For example, okay, I'll use the incline here to illustrate. Let's say that I hold the incline like so at a relatively shallow angle, and I now have the eraser at rest here on the incline. So the two surfaces, that is between the eraser and the incline, are at rest relative to each other. This then means that the force of static friction is preventing the eraser from slipping. Okay, now of course if there was no friction, then the eraser would tend to move in this direction. So then therefore opposing that tendency has to be the force of static friction acting upon the eraser, pointing up the slope. So then therefore this property here of static friction is intuitively obvious. It always opposes the direction that the object would tend to move. Okay, and then secondly, like from earlier, the force of kinetic friction, the force of static friction is independent of the surface area of contact. Once again, this makes it mathematically easy to describe. So independent the surface area of contact. Okay, and it's then with the third empirical property of static friction that we now begin to quantify it. Okay, as you'll see, however, this is a little bit tricky. The force of static friction is directly proportional to the normal force, but only when the force of static friction is at its maximum value. So the force of static friction is directly proportional to the normal force, but only when static friction is at its maximum value. This is a little bit tricky. Here's what I mean by that. Let's say once again that I use the incline here to illustrate. We'll turn this into our first quantitative example in just a few moments. Before we do, however, let's say that I hold the incline like so at a shallow angle. And then we have the following forces acting upon the eraser. We of course have gravity straight down, and we also have the normal force perpendicular to the incline, and then we have the force of static friction acting on the eraser up the incline. Right now the force of static friction acting on the eraser up the incline is exactly canceling out mg sine theta down the slope. Now let me go ahead and raise the angle of inclination slightly, like so. Right now, the mg sine theta is at a greater value than it was earlier. This then means that the force of static friction acting on the eraser here is greater than it is here. However, watch what happens the instant prior to slipping when I slowly raise the angle of inclination, like so. And then right there at that instant, right there at the instant prior to slipping, this is when static friction was at its maximum value. Only then is it proportional to the normal force. So the force of static friction acting on the eraser is not proportional to the normal force here. It's not proportional to the normal force here. It's only proportional to the normal force the instant prior to slipping. That is when static friction is at its maximum value, approximately like so. Okay, now how do we write this mathematically? We do so in the following way. Okay, so the force of static friction is always labeled as F sub S, and only when it's at its maximum value, we call this Fs max. Only when the force of static friction is at its maximum value is it proportional to the normal force. Now, like there was for kinetic friction, we have here now for static friction another coefficient. This is called the coefficient of static friction, excuse me. And the coefficient of static friction is written as mu sub s. It's once again an empirical property of the two surfaces of contact. So it's not a property of the eraser, it's not a property of the board, it's a property of the two surfaces in contact with one another. It's once again a dimensionless quantity, as it is for the coefficient of kinetic friction, and it's usually a small number. Once again, usually the coefficient of static friction is less than 1. There are some instances, like with soft rubber and so on and so forth, where it is in fact greater than 1, but if you're talking about most common surfaces that you'll encounter, usually the coefficient of static friction is less than 1. Incidentally, by the way, this is why your shoes always have rubber soles, because you want to try to make the coefficient of static friction between your feet and the floor that you're standing on as large as possible, so the floor isn't slippery. Okay, now usually for any two surfaces as well, the coefficient of static friction is usually greater than, or it's sometimes equal to, in some cases, the coefficient of kinetic friction between those any two surfaces. Here's how you can kind of visualize how this is. Let's just draw upon your own experience. In your own experience, let's say you're pushing something really heavy across the floor. Is it usually harder to get the object moving than it is to keep the object moving, or vice versa? It's usually harder to get the object moving in the first place. And the reason for that is because basically if you have a really heavy object sitting on the floor, it's like the surfaces are kind of mushed together. So you basically have to unlock those surfaces, if you will, when pushing the object across the floor. So it's usually harder to get the object moving than it is to keep it moving once it's already moving. And the reason for that is because usually the coefficient of static friction is a little bit bigger than it is for the coefficient of kinetic friction. Okay, now we'll take a look at a couple of examples here associated with static friction. Let's go ahead and look at the first of two. So for the first of two, we're going to use the incline situation here as a means of actually measuring the coefficient of static friction. It says, find the coefficient of static friction, mu sub s, if the mass on the incline slips when the angle of inclination equals 40 degrees. All right, let me go ahead and do some erasing here. Okay, so let's begin to visualize the problem like so. All right, so here's my inclined plane. Okay, right here is the angle theta, right here is the mass m. Okay, now it's actually insightful, first of all, to examine the situation if the angle is less than 40 degrees. So if the angle is less than 40 degrees and the object is just sitting here, the acceleration is 0, this then means that the forces acting on the eraser all just cancel each other out. So then we have the following. We have the normal force, like so. We have the force of gravity downwards, like so. The normal force, remember, is perpendicular to the incline. But then also preventing the eraser from slipping down the incline is the force of static friction, like so. Notice that I'm writing it as F sub s, not Fs max. The reason for that is because Fs max will occur when the angle approaches 40 degrees. Right now we're looking to see what happens when the angle is less than 40 degrees. Okay, now let's go ahead and take mg and break it up into its usual components, here and here, such that we form the angle theta. And now basically all the forces just cancel out. Once again, the acceleration is 0. So the normal force here cancels out with mg cosine theta. But then we also have here the force of static friction canceling out with the mg sine theta, like so. So the force of static friction is equal to mg sine theta. Okay, I said this earlier when I was demonstrating the situation for us. And now let's go ahead and make the angle larger. So let's now say that theta increases. So as the angle increases, mg sine theta increases, therefore static friction increases. So therefore, the force of static friction increases. And now let's see exactly what happens when the angle approaches 40 degrees. The easiest way to think of this mathematically, it's like taking a limit. We're going to take a limit as the angle approaches 40 degrees, and we're looking at the instant prior to slipping. Okay, so now let's let theta approach 40 degrees, and this is the instant prior to slipping. Only then can I now write the force of static friction as Fs max. Like so. And now it's only here that I can write the force of static friction at its maximum value as being equal to the coefficient of static friction multiplied by the normal force. I couldn't do that earlier when the angle was less than 40 degrees because static friction wasn't at its maximum value for those values of the angle. However, now that the angle is approaching 40 degrees and it's the instant prior to slipping, only then can I write Fs max as coefficient times normal force. Now from earlier on the top board, the normal force, remember, was mg cosine theta. So let's go ahead and plug that in like so. And then lo and behold, notice what happens here. The mg's cancel each other on either side of the expression like so, and then all that we have left are trig terms. So let's go ahead and move the cosine down to the denominator here on the other side. We get sine over cosine. If you recall from basic trig, of course, this is equal to the tangent of the angle theta. So the coefficient of static friction is just equal to the tangent of the angle at which the eraser slips. So then therefore I have as my answer the tangent of 40 degrees, and that ends up being about 0.84. So this example here provides an easy means of measuring the coefficient of static friction between any two surfaces. All you have to do, for example, is take the eraser, put it on the incline like so, and slowly raise it. And then right about there, the tangent of this angle here is very close to being equal to the coefficient of static friction. Once again, we have to think of this in terms of a limit, that is, as the angle approaches 40 degrees, the instant prior to slipping. One last thing here before I conclude this portion of the lecture. When I was talking earlier about the force of static friction only being proportional to the normal force when it's at its maximum value, there is a mathematical way of writing that third property. The force of static friction is less than or equal to its maximum value. Its maximum value is the right-hand side of the expression here, the coefficient of static friction multiplied by the normal force. Okay, I'll do one more example for static friction in the next portion of the lecture.